It was not created around our Sun. It came from another planetary system, crossed the enormous distance between stars, and eventually passed through our cosmic neighborhood. The object was identified as 3I, Atlas, only the third confirmed interstellar object ever observed entering our solar system. Its discovery began on July 1, 2025, when a telescope in Chile detected a faint moving object. The telescope was part of the Atlas survey, which normally searches for objects that could potentially come close to Earth. This time, however, the discovery was something far more unusual. Astronomers noticed that the object's trajectory was hyperbolic. In simple terms, it was moving along a path that could not have originated around our Sun. Instead of being trapped in a solar orbit, it was simply passing through. That meant this object had been born somewhere beyond our solar system. Before 3I, Atlas, humanity had confirmed only 2 interstellar visitors. The first was Oumuamua, discovered in 2017. Its strange shape and unusual behavior made it one of the most mysterious objects ever observed. The second was Comet Borisov, discovered in 2019. Borisov clearly behaved like a comet, but it was too faint for scientists to study its chemistry and the detail they wanted. 3I, ATLAS was different. It was discovered early enough for astronomers around the world to prepare. Hubble observed it. James Webb observed it. ALMA studied its molecules. Telescopes in Chile tracked its movement, while other instruments joined the campaign. When it was first detected, 3I, ATLAS was traveling at roughly 137,000 miles per hour. It was already inside Jupiter's orbit and heading toward the Sun. As sunlight warmed its icy surface, gas and dust began escaping from the object. This created a glowing cloud called a coma around its nucleus. The comet reached its closest point to the Sun on October 30, 2025. But despite its unusual origin, it never posed a danger to Earth. It remained well outside Earth's orbit. For scientists, however, its journey was an extraordinary opportunity. One of the first major clues came from NASA's Swift Observatory. Swift detected ultraviolet evidence associated with hydroxyl, a chemical produced when sunlight breaks apart water molecules. This showed that water was actively escaping from the interstellar comet. Researchers estimated that the object was releasing roughly 40 kilograms of water every second during that stage of its journey. But detecting water was only the beginning. Scientists wanted to know what that water could reveal about the comet's birthplace. Water contains hydrogen, and hydrogen exists in different forms. One of them is deuterium, a heavier form of hydrogen. The ratio between deuterium and ordinary hydrogen can preserve information about the environment where water formed. Extremely cold environments can produce water with higher amounts of deuterium. So this ratio can act almost like a chemical fingerprint from the comet's birthplace. Researchers used the Atacama Large Millimeter Submillimeter Array, known as ALMA, to examine the water surrounding 3I, Atlas. The result was extraordinary. The deuterium to hydrogen ratio appeared dramatically higher than what scientists normally find in comets from our own solar system. The measurement was more than 30 times higher than typical solar system comet values. That does not mean the comet contained 30 times more water. The important difference was the proportion of heavy hydrogen inside the water molecules. This suggested that 3I, ATLAS may have formed in an extremely cold environment, under conditions very different from those that produced the comets around our Sun. And this was only the first major clue. James Webb Space Telescope later provided an even deeper look. Using its infrared instruments, Webb examined the gases surrounding the comet after its closest approach to the Sun. Scientists detected water vapor, carbon dioxide, and methane. The methane detection was especially important. It was the first direct detection of methane on an interstellar object. Methane is highly volatile and can turn directly from solid ice into gas under the right conditions. Its presence around 3I, ATLAS gave scientists another clue about the object's history. The observation suggested that some of the methane was concentrated close to the comet's nucleus. That raised an intriguing possibility. The methane may have been buried beneath the comet's outer layers. During its long journey between stars, radiation could have altered the exposed surface, creating a processed outer crust while preserving older material underneath. When the comet approached the Sun, heat gradually penetrated those layers. Deeper material then began releasing gases into space. In other words, the Sun may have helped expose material that had remained protected since the comet formed around another star. Webb also detected unusually high levels of carbon dioxide. The combination of methane, carbon dioxide, and water looked noticeably different from the chemistry normally observed in solar system comets. The more scientists studied 3I, Atlas, the clearer one thing became. This was not simply a familiar comet traveling through an unfamiliar location. It was a chemical sample from another planetary system. And its chemistry was already showing scientists that planetary systems elsewhere in the galaxy may be far more diverse than. The chemical clues from 3I, ATLAS became even more interesting when scientists started examining its isotopes. Isotopes are different forms of the same element. They behave similarly chemically, but they contain different numbers of neutrons. Their proportions can preserve information about the environment where an object originally formed. Astronomers studied carbon and nitrogen inside the gases surrounding 3I, Atlas. The numbers were striking. The carbon isotope ratio was measured at approximately 147, while the nitrogen ratio was around 343. Those values were significantly different from the ranges usually observed in comets from our solar system. That matters because isotope ratios can remain largely unchanged during a comet's journey through space. They act like a record of the conditions present when the material first formed. The measurements therefore suggested that 3I, ATLAS may have originated around an older star in a chemically different region of the Milky Way. Put all the evidence together, and a fascinating picture begins to appear. The comet may have formed in the colder outer region of a planetary system, surrounded by a young star that could have existed billions of years before our Sun was born. Its environment may have been colder and chemically less enriched than the region that produced our own solar system. But how did an object from another star ever reach us? Planetary systems are not perfectly stable. As planets form and move around their stars, their gravity can disturb smaller objects such as comets and icy bodies. A close gravitational encounter can accelerate one of these objects enough to throw it completely out of its home system. Once ejected, the comet would no longer belong to that star. It would become an interstellar traveler. For 3I, Atlas, that journey may have lasted an enormous amount of time. During those years, the object would have traveled through the cold darkness between stars. Its exposed surface could have been continuously altered by radiation and cosmic particles. That may explain why some of the material detected near the comet appeared to have such a complicated history. The outer surface may have been changed over time, while deeper layers remained protected. Then, in 2025, everything changed. The comet happened to pass near our Sun. Solar heat activated its frozen materials and caused gases to escape. For astronomers, this created a temporary opportunity. They had only a limited period to study the object before it continued back into interstellar space. James Webb played a major role during that window. Its infrared instruments allowed researchers to separate the light coming from different molecules around the comet. Instead of simply seeing a moving object, scientists could examine its chemical composition. That is one of the most powerful abilities in modern astronomy. Light carries information. When molecules absorb or emit specific wavelengths, they create patterns that scientists can recognize. These patterns act like fingerprints. By reading them, astronomers can determine what materials exist billions of miles away without physically touching them. With 3I, Atlas, those fingerprints came from a world that had formed around another star. The discovery also changed the way scientists think about interstellar objects. Before 2017, humanity had never confirmed one. Then, Oumuamua appeared. 2 years later, Borisov followed. And now 3I, ATLAS has provided another opportunity to compare material from outside our solar system. The differences are already remarkable. Our solar system has been studied for centuries. Scientists have examined thousands of comets, asteroids, moons, and planets. From those observations, we have developed an understanding of what we consider normal. But there is an obvious limitation. Almost everything we have studied was created around the same star. Our Sun. 3I, Atlas gives us a completely different reference point. Its chemistry suggests that the conditions required to create planetary bodies can vary dramatically from one stellar system to another. That means there may be no single universal recipe for building comets. Some systems could create objects rich in methane. Others may produce bodies with unusual water chemistry. Some could form in extremely cold environments, while others may develop under very different temperatures and radiation conditions. The possibilities are enormous. And 3I, ATLAS may be only the beginning. Future observatories could discover many more interstellar visitors. The Vera C. Rubin Observatory is especially important because it repeatedly scans huge portions of the sky. Its long-term survey should make it much easier to identify faint objects moving through our solar system. If more interstellar objects are discovered, scientists will finally have enough examples to make meaningful comparisons. Imagine finding 10 different interstellar comets. Then 20. Eventually, researchers could begin asking whether the unusual chemistry of 3I, Atlas is common or extremely rare. Every new object could provide another sample from a distant planetary system. And each sample could answer questions that spacecraft may never be able to reach directly. Because traveling to another star is incredibly difficult. An interstellar comet solves part of that problem naturally. The object does the traveling for us. It crosses the galaxy, enters our solar system, and gives our telescopes a chance to examine